Okay, we'll start. Let me share my screen. Is the screen visible? Elizabeth? Yeah, okay. Yeah. So, welcome to the seventh week of this course. So, week 7 means we are officially entering the second half of the course. So, first we'll start with some recap as we do every time. So, uh, at the end, we had seen last week that rigid body has total 6 degrees of freedom, right? We knew the definition of rigid body. It's that distances between the particles do not change or do not change significantly, right? And so the bifurcation for 6 was 3 for translation. So you can move your object anywhere in the space. That's your translation. Plus 2 for deciding the axis of your rotation. So it can be point in any direction. So you need one polar angle and one azimuthal angle. So that is theta and phi. For axis, fixing an axis. Once you fix axis, you can rotate about that axis. So that gives one more angle to rotate, right? Angle about axis, right? So if you say fix a point, then you are killing the translation. So you are killing 3 degrees of freedom. You have just 3. If you fix the axis as well, then you are killing 2. You are left with 1. If you fix the angle also, then there is nothing left. You have perfectly described the system. There is no degree of freedom. Okay. So then we started with rotations in 3D, right? So the idea was that we have a frame XYZ, right? And there is a vector R that is rotated to some other vector R prime. And not just this vector, every vector is rotated accordingly. So we can say that entire coordinate axis is rotating, or other way of saying that is that there is a rigid body that is being rotated, and R can be written as some matrix A, sorry, R prime, the new vector, times the vector R, and the properties of A were it's orthogonal, and therefore all the properties of orthogonal symmetric matrices. One was that determinant of A should be plus or minus 1, right? The third is that, okay, about eigenvectors, so we will talk about them later. But so the idea is let's do some examples to see, let's have some intuitive feeling about it. So we have I, J, and K, right? These are our unit vectors. Suppose I want to go from this to this. This is K, this is I, and this is J. Can I do it continuously or not? So I have I, J, and K, and if I rotate this by 90 degree and by this by 90 degree, you can imagine that you can actually do that, right? So these are called proper rotations, in which you can continuously move your axis to another one, right? So we can call this I prime, J prime, and K prime. Another example would be something like this. This is your I, J, and K, which goes to K. This is J. This is I prime. Now, can you do such a rotation in space? And the answer is no, not possible just by rotation, right? By rotation. So this is improper transformation. So in both of the case, the matrix that transforms initial to final are orthogonal. But for proper, we have determinant of A as plus 1, right? And the reason is that the identity matrix belongs to this group. So we have divided the set of orthogonal matrices into two groups. One, those are proper, and the others, those are not proper. For this, we will have mod A is equal to minus 1 magnitude. Or you can think of another one in which you are just flipping I. So this is your I, this is J, and this is K. Clearly, you can't do it continuously just by rotating, right? You need to flip or reflect, which gives this minus sign. Okay, so that said, we have talked about Euler angles. I mean, the professor has talked about it in a great detail. So what I want to do is just give a feeling from a different perspective. So what we start with is we have three vectors I, j, k, right? And then we are shifting it to I prime, j prime, and k prime, right? They are still orthogonal 90-degree, okay, but rotated. So since I prime is also a vector, it is a linear combination of I plus j plus k, right? So there must be some numbers that are here, and what are those numbers? So if I put I prime here, I can say this angle is some theta 1 1. The angle with j is theta 1 2, and with k theta 1 3. Then I prime would be simply cos theta 1 1 I, because that's the component along I axis. Then cos theta 1 2 and cos theta 1 3 k, right? Similarly, I can write for j prime also cos theta 2 1, which is the angle between this j and I, j prime and I, right? Etc. So I'm not writing in k prime also. So it looks like we have total 9 angles: theta 1, theta 1 2, theta 1 3, theta 2 1, theta 2 2, theta 2 3, and theta 3 1, theta 3 2, theta 3 3. Right. So it looks like we have 9 coordinates. If you clearly, if you specify all these angles, task is very easy. Just use this transformation. But the next question is, are they really independent of each other? Meaning, do I really need to know all 9 of them? And the answer is no, which means the degrees of freedom is less than 9. And why do we care about it? Because we know that for Lagrangian, we have to write it in terms of independent coordinates, right? Generalized coordinates. So, what are the dependencies in the system? That is given by the fact that I prime, j prime, k prime axis is also orthonormal, right? So they are perpendicular to each other, and the unit vector stays unit vector. So we have I prime mod of I prime as 1, which will give us whole square cos square theta 1 1 plus cos square theta 1 2 plus cos square theta 1 3 is equal to 1, right? So that is one constraint, right? This is constraint. So that is your first constraint. Second would be same for j prime square. So we will have 1 2 2 2 and 2 3. Sorry, 2 1 2 2 and 2 3. That will be equal to 1. So that is one more. Third is k prime square is equal to 1. So it is 3 1 3 2. and 3 being equal to 1. So, okay, so now we have three constraints. We know that there are only 3 degrees of freedom, right? The Euler Angles. So, where are other three constraints? So, that comes from the ortho part of the system. We talked about normal. These all are normal vectors. So, the fourth would be that I prime dotted with j prime should be equal to 0, which means if you look at this, I prime, if you dot both this, you get cos theta 1 1 times cos theta 2 1 plus this times this plus this times this, right? So you have cos theta 1 1 cos theta 2 1 plus cos theta 1 2 cos theta 2 2 plus cos theta 1 3 cos theta 2 3 is equal to 0. So that is one constraint. Similarly, we have j prime dot k prime, right? Which gives another constraint, and k prime dot I prime is 0, which again gives. So all in all, we have, so we need to choose pairs, right? That pair should be orthogonal. So we have 3C2, which is 3. So now the degree of freedom is total 9 variables, out of which 6 are constrained, which means we have 3. And Euler angles is one of the ways you can describe those angles, Euler angles, which were what? Phi, theta, and psi. So if you tell me these three angles, I can convert them into theta 1 1, theta 2 1, etc. Okay, so that was the idea. And how were Euler angles defined? So we had this procedure, right? If you remember, you take x to the normal line and do again one other rotation so that your z is set properly, and then you again do rotation so that x and y are set properly. So I don't want to repeat that, but rather I want to show you a video, because word is, a picture is worth 1,000 pictures, 1,000 words, and a video is worth 1,000 pictures. So you start with your system x0, y0, z0, and you want to go to x1, y1, and z1. So first rotate about your z-axis by some angle psi. Okay. Then you start rotating about your new x-axis, which they call x1, by some angle theta, such that this z aligns with z1. Okay. So the now we can answer how much psi should be. It should be such that when rotated after the rotation of psi, if we rotate the system about this x1, the z should be able to go to z1, right? And that happens when you have your x1 aligned in the intersection of both these planes, your new xy plane and old xy. So in our lectures we had phi or theta instead of psi. Okay, so once it is aligned to x1, then rotate about x1 so that your z0 is set to z1, and the final step is to rotate about z1 so that this doesn't get changed, and your x1 x goes to x1. Okay, so you can, it's on YouTube, you can just see. But basically at the end, you go from your x0 to x1, z0 to z1, and in doing so, you ensure that y0 automatically goes to y1, because once you set x and y, x and z, any two coordinates, the y is already set, right? Because it has to be perpendicular to both of them, and we know that it can only point in one direction because it's our right hand convention, and that will ensure that determinant of a is positive 1. Okay, so
So just to
yeah,
clarify one thing about
yeah,
the Euler angles. So
yeah,
when we're deriving the Euler angles, the idea is I am trying to align the body set of axis with the fixed coordinate system, correct? The
yeah,
space set of axis. That
right,
is what I'm okay,
right.
okay. got
So that is one way of thinking. Another way of thinking is that you are aligning your axes themselves. You are changing your coordinate system itself. So your new axis,
got it.
both are equivalent, but there are two ways of
Okay,
thinking. And if you are
sure,
interested
sure.
more, there is a discussion in Goldstein which talks about these two approaches. Okay.
Okay,
Yeah.
sure. I will look
Yeah.
at it. Thank you.
So basically, we have a recipe to go from XYZ to what they called? I think psi, eta, and zeta, right? If you these are new characters for you, this is psi, pronounced as xi. This is eta, and this is zeta, because sometimes people do get confused. Okay, so and it was done in three steps. First was to rotate about your z-axis by some angle phi, right? Then in second step, you rotate about your x1 axis, which was called psi prime, I think, in the lecture, by some angle theta. And the third one is rotate by rotate around your z-axis, yeah, or z prime axis with some angle psi. Okay, so we can finally go from r to r prime with this phi applied in r, then apply this rotation, which we call theta, on this entire thing, and then apply psi. And we derived what should be the components of this matrix. By the way, since matrix multiplications are associative, we can just write this as psi, theta, and phi operated on R. Okay. So this entire matrix is your matrix A that takes you from R to R prime. Okay. Um, then did we have anything about rotation? Yeah. So there were four results that we saw. One was if V is eigenvector, writing in shortened notation, then V star also is also an eigenvector. And A2 was if lambda is eigenvalue, then lambda star is also eigenvalue. And for that, with eigenvector V star. Okay. Third was V mod lambda square for any I is 1, which means in a complex plane it lies on a unit circle. And the last one was that at least one lambda k is equal to 1 for at least 1k belonging to 1, 2, 3 or xyz. Right? So we have three eigenvalues, all of them lying on this unit circle. So this is real axis, this is imaginary. But all of them, if they are there, then their complex conjugate should also be there. But we have only three of them. So what can happen is if we have this one, this is your lambda, then lambda star also is there. And now there is only one value. It has to be real. So it has to be 1 or minus 1. And then we know that determinant is 1, which means the product of all of them is 1. The product of lambda star times lambda is 1 because that is your mod lambda square. It means it has to be 1, the third one. Okay. So these three are your eigenvalues, and correspondingly you have eigendirections, which means there exists a direction R such that this matrix applied on R does not do anything because eigenvalue is 1. Okay. and you can show that this direction is also real. Okay, which means we can define axis of rotation. Now this might sound intuitive, and then if you think of more, then it may not sound intuitive, because if you generally we think of rotation as spinning constantly with some angular velocity, and clearly you can define axis. But what if it is doing some random dance in space? Even then, instantaneously you can always define an axis of rotation. Rotation, right? And that is your eigenvector with eigenvalue 1. Okay, and uh, so this is the only real direction in which there is eigenvalue. So the only real eigenvector. It means that all of them are changing the direction, which is what happens in the rotation, right? If you have a fixed direction, fixed axis, all other directions are changing. Only this one is constant. So where are other two directions, other two eigenvectors? They are in the complex plane. Okay, and then so this was your Euler's theorem, that effect of rotation can be thought of as a rotation about an axis, right? And then we started looking at motion. So we derived one thing, that velocity of a particle in an inertial frame is the velocity of center of mass plus a vector which we call omega, that is your angular velocity, cross r, right? Where r is, so you have something, and this is your r prime, and this is your center of mass or any fixed point. So this is your r. Okay, so velocity is measured in inertial axis, that is with respect to this one, and omega cross r is this thing, where omega is pointing in some direction that we so right, this one is eigenvalue, eigenvector. Okay, and then we discovered that we can do a transformation from r going to r plus a, and so there exists an a such that what happens is this velocity has a parallel component parallel to omega, right? And plus omega cross r. So there is no perpendicular component of center of mass in that frame. So there exists some point which need not be at the center of mass. Okay. So I was thinking of how can we imagine it visually. So one example would be you have sun and you have earth orbiting it. So there is a plane, right? So earth is moving in this direction, but it is also rotating. But very importantly, it's not rotating at an axis that is perpendicular to this plane. Rather, there is an angle about 23 degrees, right? So the rotation is not perpendicular to plane. So you can imagine there must be a point somewhere, could be inside the earth or outside, from which momentarily the velocity looks parallel to your omega. Okay, and this was your uh, Chesel's theorem, right? And we should keep in mind that this can change. Even omega itself can change with time. So this is at a given time, right? Um, Anything else? Yeah, at the end we just talked about, as a prelude to next week, angular momentum. So L, which is just defined as sum of m r cross v, right? Or rather r prime if you are looking from this. And then when you expand, you see that it is angular momentum of center of mass plus a term that is due to rotational term. And this rotational term when we expand and use the properties of cross product was I k times omega k, right? Where I k is some matrix called tensor of inertia, yeah, or momentum, something. So in 11th, when we were kids, we used to write L as I omega, where with this was some number, omega is another number, right? And even in vector notation, L was proportional to omega. So now this was some vector, but this was always a number. Now we see that that is not the case. For a general case, you can have L not proportional to omega. Rather, you can have mixings of these components of omega, and that is exactly what this is doing. So if you look at L1, it will have something times omega 1 plus something times omega 2 plus something times omega 3. And these somethings are your components of tensor, right? I1, 3. Okay, so yeah, that's all. We can write explicitly what IIK was. It was sum of mass delta IK R square minus RI RK, right? So that's all we did this week. Now let's try to solve some questions. Before that, does anyone have any question for this discussion? Okay, I guess not. Then let's start with assignments. So the assignment questions are, by the way, pretty trivial. Most of you should be able to do it on your own. Nevertheless, let's just have a look together. So the first one is, how many degrees of freedom does a free symmetric top have? So the top is free, so it can be in any direction, anywhere. So you have 3. Still, you can point its axis anywhere, so 2, and you can make any rotation, right, by any angle. So it's a free thing. So it has 6 degrees of freedom. The symmetric does not mean anything here. I mean, does not change the fact that it has still 6 degrees of freedom. Okay. So the second question is, how many degrees of freedom a symmetric top has, which has one point fixed. Okay. So let's say the bottom point is fixed, which means now it can only decide the direction of axis, which can be anything, and how much it is rotated about that axis. So you have 2 plus 1. Basically, you get the translation degrees of freedom. Okay, so it's 3. Third one is, 2 points along its axis are fixed. Okay, which means the axis is basically fixed. So now you have this thing, but earlier you had freedom of choosing which axis it is. It could be like this as well, right? So now you don't have that freedom. So the only freedom is by how much angle you can choose. So you just have 1 degrees of freedom, which is this phi, right? In this case, we had phi and we had this theta and phi prime for the axis. Okay, the fourth one is, consider a symmetric top. 3 non-collinear points are fixed. Then how many degrees of freedom it has? Okay, so let's think about it. Suppose we had 3 collinear points fixed. So now, like previous case, the axis is fixed and it has this degrees of freedom. But now the points are not collinear. So let's say this was fixed, and the third one was this. So earlier it could have this freedom of being anywhere, but now this is fixed, which means that there is no degree of freedom, right? Because you fixed your axis and you fixed the orientation about that axis as well. So you have completely told me where the top is where the every molecule of the top is. Okay. So sorry. So it has 0 degrees of freedom. Okay. So now uh, this is a nice question, physics question for the first time, because what we did so far was just pure mathematics, right? We did not invoke any physical principle. It was purely mathematical. So this is, think of a copper block as a truly rigid body. Okay. That is that the distances between its points are assumed to be fixed, total. Can this block absorb heat? So if the atoms are fixed, the distances cannot change. It means what happens if we give it heat? Its energy changes, right? There is vibration, and there is velocity of these particles. In fact, average velocity is proportional to the temperature. We know this, right? But what we are saying is that they are not allowed to have velocities, which means that it cannot absorb heat. So this cannot absorb heat, which also means one thing, that we have at room temperature or any finite temperature, we should have some average fluctuations. So no body is truly rigid, no matter how you make it, or as long as there is some temperature, there is some vibration. So that's what I meant when we defined our rigid body as the distances should not change significantly. Okay. If it is truly rigid, it does not exist. It's a joke. Okay, sixth one, now slightly mathematical. Consider the set of orthogonal transformations. Is the following statement correct? Identity matrix is continuously connected to this matrix. Okay, so there are two ways to answer this. First is, we had seen that what it is asking is basically, is it proper? That means, can we rotate something by this much matrix? So that can be determined by the determinant. Clearly, it's minus 1 into minus 1 into minus 1. So minus 1, which means improve, right? So it's wrong. Another way, which is slightly more intuitive, but it cannot be used every time, is that suppose you apply this matrix minus 1, minus 1, minus 1, rest of them 0 to x, y, z. What do you get? So you get minus x, minus y, minus c, right? This is basically minus I or 1. So which means if you add this x, y, and z, it will become x, y, and z, right? Now, can you do this? No, because if you, let's say, rotate this about your y-axis so that x is aligned, and then rotate about z-axis so that y is aligned, you will see that your z-axis is towards here, not the other way, right? So it's not possible. So this gives a pictorial way of thinking. This last one is probably the most difficult of these examples, nevertheless very easy. So the question is, there is some transformation rotational matrix A at starting time t0, and one of the eigenvalues are is given, lambda 1 is given as 1 plus I by root 2. What are the other eigenvalues? So we know that if z is eigenvalue for lambda, then lambda star is also a eigenvalue. Okay, so lambda 2, which is your lambda 1 star, should be the eigenvalue, which means 1 minus I divided by root 2, right? You change the imaginary part, flip the sign, but the real part stays the same. Okay, what about lambda 3? We know at least one of them has to be unity. So lambda 3 is unity. Or you can just say the product of all this should be 1. Okay, so 1 is 1 and another is 1 minus I by root 2. The first option. Okay, and those were the questions from the last time. Uh, any comments or questions from your side? Elizabeth or Sumit?
I do not have anything from my side.
Okay. Elizabeth?
Everything is clear, sir.
Oh, okay. Awesome. Then maybe we should stop here and let's meet next week. We'll continue the discussion on rotations and tops. Okay. Sure.
Harsh,
Bye.
could you please
Yeah.
share these PDFs somewhere? I don't see the PDFs anywhere, so if you can just share them, it would be easy for me to
Yeah,
revise
yeah. So,
these
have you
things.
access to that Google Drive folder which I had shared in the first class?
No, I did not. Is it there on the announcement? I have not seen that
I
PDF for
don't
that
think it's
reason.
there on the announcement. Let me quickly see. You can see my screen, right? So
Yes, I can.
let me show you the QR code. Scan it. I'll upload the slides there. Okay. Oh wait,
Okay,
maybe I don't have it here. Just a second. Give me a moment. Should we send it? So this. No. Let me generate it right now.
sure.
This. I don't know where it went. Oh wait, I can show you the link. Okay. This link. If only it opens. Okay, you can do one thing. You know my YouTube channel, right?
Yeah, I know.
Yeah, so in that, go to the first class.
Mm-hmm.
In that, I have shown you the QR for this folder. Okay.
Okay, okay, sure,
Yeah.
sure.
So I haven't uploaded last few weeks. I'll do that by tonight. Okay.
Okay, sure, sure.
Yeah,
That
it also
helps.
has this notebooks, Mathematica notebooks if you want to. Okay.
Okay, okay,
Yeah.
nice. Yeah, thank you.
Okay.
That will help.
Chalo. Let's meet next
Yeah,
same time.
yeah.
Bye.
Bye, bye.